Hello everyone, my name is Armando Mendez and I'm here to present our research titled Multimodal Breast Ultrasound Segmentation, Combining Visual and Clinical Data. This work was conducted in collaboration with my professors Ming Xu and Dr. Quang Huang at Keene University. Our study focuses on improving the segmentation of breast ultrasound images, a critical step in the early detection of breast cancer. We aim to bridge the gap between visual imaging and clinical data, combining the strengths for both for enhanced performance. To start, breast cancer is one of the most prevalent forms of cancer affecting women worldwide. Early detection is crucial for improving survival rates and medical imaging techniques, particularly ultrasound imaging, playing a vital role in identifying and diagnosing breast lesions. Several approaches have been explored to improve breast image segmentation performance further. To further improve breast ultrasound image segmentation and capitalize on the success of multimodal image segmentation, we explored integrating both image and textual data in this research. Now, let's take a moment to look at the data on cancer in women in the United States for 2024. Breast cancer, as you can see in the diagram provided below, is the most commonly diagnosed cancer in women, with over 310,000 estimated new cases in this year alone. That's nearly one-third of all new cancer cases in women. Tragically, it's also the leading cause of cancer-related deaths, responsible for over 42,000 lives lost, accounting for 15% of cancer deaths. This data speaks with the dual challenge we face. While breast cancer is often detected early, saving lives, its prevalence remains alarmingly high. It's a stark reminder of the importance of regular screenings, public awareness, and the ongoing investment in research. If we were to reduce both the number of cases and lives lost, we would need to focus on prevention, early detection, and the access to the best treatments for every woman, no matter her circumstances. Looking at the breast cancer incident rate, the trends in breast cancer incidence tell a compelling story. Since the mid 2000s, the overall breast cancer rate has been gradually rising. This increase is partially due to shifts in risk factors, including higher rates of excess body weight and changes in childbirth patterns, such as having fewer children or delaying childbirth. From 2012 to 2021, breast cancer cases grew annually about 1% among white, black, and American Indian slash Alaska Native women. Meanwhile, the increase was more pronounced among Hispanic women at 1.6 and highest among Asian American and Pacific Islander women at 2.6 per year. It's also important to note that white women consistently have the highest incident rate of breast cancer. These patterns highlight the need for targeted prevention efforts, culturally specific education, and equitable access to care to address the unique risks and challenges faced by different communities. Looking at the breast cancer death rate, since 1989, we've seen a significant achievement in breast cancer treatment and awareness, a 44% decline in breast cancer death rate, largely driven by advances in early detection and improved treatment. However, this success story has not equally experienced by all women. The data shows a persistent disparity between black and white women in breast cancer mortality rates. While death rates have declined for all groups, black women consistently have a higher mortality rate than white women. These disparities stem from inadequacies in access to resources such as ultrasound screenings, early diagnosis, and high quality treatment. The gap underscores the critical need for equality in healthcare. If we are to make further progress in saving lives, we must address these systematic barriers and ensure that every woman, regardless of race or ethnicity, has the access to the same level of care and opportunities for early intervention. Moving on to our contributions in this research, we introduced an innovative network called U-Swing that integrates convolutional layers with transformer architecture to enhance bus image segmentation. We also proposed a multimodal segmentation method that utilizes U-swing, combining clinical data with the Burr and Clip model. We also assessed our techniques using a publicly available bus image data set, and we also tested different forms of clinical information as text inputs to identify which ones would enhance bus image segmentation the most. Moving on to our methodology, below is a diagram showing our U-swing architecture that would perform image segmentation along with processing also clinical information from our Burr and Clip models. Our U-swing architecture combines the U-swing transformer V2 as an encoder with a custom decoder to process and reconstruct images. The encoder will begin by breaking down a 224 by 224 input image into smaller patches and extracting hierarchical features through the 5 convolutional blocks, which are labeled in green in our diagram. These blocks compress the image into progressively smaller yet more detailed feature maps, which are labeled F1 to F5 in our diagram, capturing everything from fine textures to overall structures. At the final convolutional stage, the model will then integrate clinical text information such as tumor classification, BI-RAD scores, and tumor shape via our Burr or Clip model, adding enriched context for segmentation. The decoder, consisting of 5 deconvolutional blocks, which are labeled orange in the diagram, reconstructs the image by progressively upsampling the feature maps to the original resolution. Skip connections transfer crucial details from earlier encoder stages directly to corresponding decoder stages, ensuring no information is lost during the reconstruction. By combining visual features from the encoder and contextual embeddings from the text models using element-wise operations, the model enhances its segmentation accuracy. The final output is a high-resolution segmentation map that accurately highlights the specific regions of interest, such as tumors. Our multimodal approach is able to integrate both visual and clinical insights, making the U-swing architecture suitable for tasks requiring precision and detailed analysis, such as breast ultrasound imaging. Moving on to our experiment, we utilized an online public data set named Breast Lesions USG-BLU to evaluate our methods. The data set included bus images and segmentation labels that are used for supervised learning. They also contained a total of 256 images, which were each paired with a ground truth segmentation mask used to detail the tumor infected region. The type of images in the dataset were also breast ultrasound images. Continuing our experiment, in addition to the breast lesions USG BLU dataset, they also provided a clinical Excel sheet filled with information for each case. Some of the major columns would include a case ID, which is a unique number used to link the ultrasound images with its clinical data, along with clinical attributes. For this column, it provided various clinical attributes such as the patient's age, the type of tissue within the breast, the tumor shape, BI-RADS, which is the likelihood of malignancy, the tumor's classification, which were then labeled either benign or malignant, and etc. Before inserting the images into the models, they were also each sized to 224 by 224. And lastly, the dataset was randomly split so that 80% would be used for training and 20% would then be used for testing. Moving on to our experiment settings, all of our models were trained using the PyTorch 1.13.1 on a system running Ubuntu 20.04, which was also equipped with an Intel R Xenon W-223 CPU with a 3.60 GHz CPU, along with one NVIDIA RTX 4080 generation graphics card with 20 GB of memory, and two NVIDIA RTX A2000 graphics cards, which each held 6 GB of memory. To ensure fair comparisons, we made sure to train all of our models under the same settings. For the loss function, we used the cross entropy loss across all of our models. A consistent training protocol is followed, with each model trained for 50 epochs using a batch size of 8. The atom optimizer is employed with a learning rate of 10 to the power of -4 and a weight decay of 10 to the power of -4. Continuing our experiment settings, we compared our method alongside other recent and well-known segmentation methods, these methods being swing UNet, trans UNet, segment anything model, SAM, and efficient SAM, ESAM. For each of our clip or BERT models, we also explored the impact of different combinations of the clinical information, such as, for example, U-swing plus clip 1, which would utilize all available clinical information, U-swing plus clip 2, which would utilize only the classification and BRADS columns, U-swing plus clip 3, which would utilize classification, shape, and BRADS only, U-swing plus BERT 1, which would then utilize all available clinical information, U-swing plus BERT 2, which would utilize only classification and BRADS, and lastly U-swing plus BERT 3, which would utilize only classification, shape, and BRADS. Moving on to our metrics. To assess the performance of our models, we utilize the calculation of intersection over union for both the breast tumor and background areas, while also calculating the mean IOU for our models. The tables provided below will show the ablation study for the BERT and clip-based multimodal framework. For our first figure on the left, we can see the ablation study for our BERT-based multimodal framework. For this framework, we tested the regular U-swing model along with U-swing plus BERT 1, U-swing plus BERT 2, and U-swing plus BERT 3. Looking at our tumor IOU, background IOU, and mean IOU, we can see that U-swing plus BERT 1 showed to have the most effective results. On the table to the right, we then see our other ablation study for our clip-based multimodal framework. We also assessed the U-swing model along with U-swing clip 1, U-swing plus clip 2, and U-swing plus clip 3. Looking at the tumor IOU, background IOU, and the mean IOU, we can see that the U-swing plus clip 3 showed to outperform the other models. Moving on to our overall performance, the figure on the right compares different models highlighting the performance of the proposed U-swing plus BERT with all clinical information against a single modelly segmentation methods such as swing UNet, trans UNet, SAM, and ESAM. The proposed model achieved a tumor IOU of 0.6711, a background IOU of 0.9717, and a mean IOU of 0.8214, outperforming swing UNet, trans UNet, and SAM across all metrics, while ESAM attained the highest tumor IOU being 0.6878 and a mean IOU of 0.8381. The proposed method demonstrated competitive results, particularly excelling in background segmentation. These findings underscore the effectiveness of integrating clinical information through the BERT-based multimodal framework, which enhances segmentation accuracy and establishes a strong baseline for future work. Continuing our overall performance, the figure to the left will show the segmentation results of different segmentation models. In the figure, we can see 3 examples of segmentation results. Column A shows the original images used. Column B will show the ground truths. Column C will show the U-swing, which is the baseline single modelly. Column D, which shows the U-swing plus clip 1. Column E, which shows U-swing plus clip 2. And column F, which shows U-swing plus clip 3. In conclusion, this study proposed U-swing, a hybrid U-shaped network combining convolutional layers and transformers for breast tumor segmentation in ultrasound images. By integrating clinical text information using BERT and CLIP, The model achieved improved segmentation accuracy, outperforming swing UNet, TransUNet, and SAM while remaining competitive with eSAM. These results highlight the potential of multimodal learning to enhance medical imaging and early breast cancer detection, with future work focusing on refining the framework and testing on diverse datasets. For our acknowledgments, this project was partially supported by the Office of Research and sponsored programs at Kean University, along with support from the Cassie Google Institutional Research Program for the 2024 to 2025 period. I would also like to acknowledge our team, which consists of me, Armando Mendez, and my professors, Dr. Quang Huang and Ming Xu. Thank you.